Look up at the night sky. What do you see? A vast, dark canvas sprinkled with tiny, shimmering lights. For thousands of years we have gazed at this cosmic ocean, filled with wonder and a deep sense of curiosity. We have told stories about the stars, charted their movements, and dreamed of what lies beyond our own small world. Each point of light is a distant sun, perhaps with its own family of planets. Each faint smudge could be a galaxy containing billions of such suns. The universe is a place of endless mystery and boundless possibility, a grand theatre where the story of everything is constantly unfolding, and we are just beginning to read the first few pages of this incredible epic. This innate human desire to explore, to understand our place in the cosmos, is what drives us forward. It is the same spirit that led our ancestors to cross vast oceans and explore new continents. Today, our ships are not made of wood and sail, but of metal and circuitry, and they travel not across water, but through the vacuum of space. One of the most magnificent of these modern-day vessels of discovery is the James Webb Space Telescope. So what exactly is this mysterious object, 3I Atlas? The I stands for Interstellar, which tells us this object is not from around here. It is not part of our solar system's family of planets, asteroids, comets that have been orbiting our sun for billions of years. Instead, 3I Atlas is a tourist, a visitor from another star system that has traveled an unimaginable distance to pass through our neighborhood. The 3 means it is the third such interstellar object we have ever confirmed. Oumuamua, Borisov, and Atlas is the name of the survey that discovered it, the Asteroid Terrestrial Impact Last Alert System. When astronomers first spotted 3I Atlas, it was just a faint, fuzzy dot moving through space. But by carefully tracking its path, they made a startling discovery. Its trajectory was not a closed loop, an ellipse, like the planets and asteroids in our solar system. Instead, it was on a hyperbolic path, a wide, open curve. This meant it was moving too fast to be captured by our sun's gravity. It was simply passing through, destined to swing around our star and then head back out into the interstellar void, never to return. To understand the discoveries about 3I/Atlas, we first need to appreciate the incredible instrument that made them possible, the James Webb Space Telescope, or Webb for short. It is not just another telescope, it is a marvel of engineering. Launched on Christmas Day 2021, successor to Hubble, but it sees the universe very differently. Hubble, visible light. Hubble, ultraviolet light. Webb, infrared. Infrared is the key, a veritable time machine. Why infrared? Infrared is heat radiation. It reveals things that are too cold, too distant, too hidden, like night vision goggles for the cosmos. Light from the most distant galaxies travels billions of light-years. Cosmic expansion stretches its wavelength, shifting visible light into infrared. In infrared, Webb sees first stars, early galaxies. It also pierces thick cosmic dust to reveal birthplaces of new stars and planets. Webb's design is iconic. Primary mirror, 6.5 m across 18 hexagonal segments coated in a thin layer of gold. Gold reflects infrared, hence the golden hue. A giant 5-layer sunshield the size of a tennis court. The shield blocks light and heat from the Sun, Earth, Moon, letting Webb stay frigid and ultra-sensitive. The moment astronomers had been waiting for finally arrived. On September 1, 2025, the James Webb Space Telescope turned its golden eye towards 3I Atlas. The object was already on its way out of the solar system, a small, faint blip against the backdrop of distant stars. The telescope's instruments locked on, gathering every precious photon of infrared light that had traveled from this interstellar messenger. The data streamed back to Earth, to the Space Telescope Science Institute in Baltimore, Maryland, where teams of scientists eagerly awaited the first results. What secrets would this piece of another solar system reveal? The anticipation was electric. The very first images and spectra were breathtaking for the information they held. Webb's incredible sensitivity captured detail impossible before. Initial data confirmed that 3I Atlas was comet-like. As it got closer to our sun, ices on its surface sublimated, turning solid ice directly into gas. That created a fuzzy atmosphere, a coma full of gas and dust around the object's solid nucleus. Webb analyzed light passing through this coma, giving a direct probe of the object's composition. One of the first and most fundamental things scientists looked for was water. Water is crucial for life as we know it, and understanding its abundance in other star systems is a top priority for astronomers. Using its NIRSpec instrument, Webb analyzed the infrared signature of the gas in the coma. The results were clear and unambiguous. Water vapor was present and it was plentiful. The characteristic fingerprint of H2O molecules was stamped all over the spectrum. This was a hugely significant finding. It provided the first direct, concrete evidence that the building blocks of our own solar system's oceans and life are also present in other planetary systems. But Webb didn't just find water, it was able to measure its properties. Water ice can exist in two main forms: amorphous, crystalline. Amorphous ice forms when water vapor freezes very rapidly at extremely low temperatures. The molecules are jumbled and disordered. Crystalline ice, like ice cubes on Earth, has molecules in a neat hexagonal lattice. To form crystalline ice, the water needs to be warmer, above about -120 degrees Celsius, for a period allowing molecules to shuffle into place. Webb's MIRI instrument detected the clear signature of crystalline water ice on 3I Atlas. This was not the disordered amorphous ice many expected on an interstellar body. The presence of crystalline ice implies the material was heated to allow that structure to form. The protoplanetary disk where this object was born wasn't just frigid and static. Heat, processing, activity, the surprises didn't stop there. Webb is also a master at detecting organic molecules, the carbon-based building blocks of life. The spectrum from the coma showed unmistakable fingerprints of several organics: methane, methanol. Then a more complex signature appeared. It was identified as glycolaldehyde, a simple sugar molecule. Glycolaldehyde is a precursor to ribose, the R in RNA. While the presence of water and simple organics was exciting, it was another discovery that truly stunned the scientific community and challenged our existing models of solar system formation. As Webb's spectrographs dissected the light from 3I Atlas, they searched for the signatures of various elements: carbon, oxygen, nitrogen. But what they didn't find was just as important as what they did. The data revealed a striking and almost complete absence of carbon monoxide ice within the object. This was a genuine shock to the system for planetary scientists. In the cold outer reaches of a young solar system, where comets are born, carbon monoxide freezes easily and should be one of the most abundant ices after water. We see it in almost all of the comets from our own solar system's Oort cloud and Kuiper belt. For 3I Atlas, to have so little of it was bizarre. It was like baking a cake and finding it contained almost no flour. It immediately told scientists that the environment where this object formed must have been very different from our own. This unexpected finding sent theorists scrambling back to their models. How could an object form with plenty of water and complex organics, but almost no carbon monoxide? One leading hypothesis is that 3Y Atlas formed in a part of its home protoplanetary disk that was unusually warm. In this warmer region, perhaps closer to its young star, the carbon monoxide would have remained a gas instead of freezing into ice. The discoveries made by Webb on 3Y Atlas are not just about a distant alien object. They hold up a mirror to our own origins. By studying this visitor, we learn more about ourselves and our place in the galaxy. The presence of crystalline water ice and complex organic molecules like glycolaldehyde strongly suggests that the fundamental building blocks for watery, life-bearing worlds are not a fluke. They are likely common ingredients throughout the cosmos. This bolsters the idea that the universe is probably teeming with planets that have the right raw materials for life to begin. It makes the prospect of finding life elsewhere seem a little less remote. The comparison between 3I Atlas and the comets from our own solar system is particularly enlightening. Its water has a deuterium to hydrogen ratio similar to Earth's oceans. That adds another piece to the puzzle of where our planet's water came from. For a long time, asteroids were considered the primary delivery mechanism. Many comets we had studied didn't have the right water ratio. But if interstellar comets like 3I Atlas and perhaps a whole class of comets in our own system do match this ratio, it reopens the debate. Earth's water could have been delivered by a diverse fleet of cosmic objects from within our solar system, and even from outside it. However, the surprising lack of carbon monoxide forces us to be humble. It reminds us our solar system is just one example among billions. It introduces a new variable into planet formation models. Perhaps the planets from 3I Atlas's system are chemically very different from ours. This diversity is a crucial concept. Expect a wide variety of planetary systems out there, some like ours and some unimaginably different. Planet formation isn't one story, it's a grand anthology. As 3I Atlas continues its long journey back into the darkness between the stars, it leaves behind a wake of excitement and a wealth of new questions. Its brief passage through our solar system, illuminated by the powerful gaze of the James Webb Space Telescope, has fundamentally altered our perspective. We have peered into a time capsule from another star system and found familiar, life-giving ingredients mixed in a surprisingly unfamiliar recipe. This single encounter has underscored both our cosmic connection and our cosmic uniqueness. It's a humbling and exhilarating reminder of how much there is still to learn. The success of these observations is a testament to human curiosity and our relentless drive to explore the unknown. For centuries, we have been limited to studying our own cosmic backyard. Now, for the first time, we have analyzed the pristine material of another world, born in the cradle of another star. This is a pivotal moment in the history of science, akin to the first time Galileo pointed a telescope at Jupiter and saw its moons, proving that not everything revolved around the Earth. We are once again expanding our horizons, realizing that our solar system is not an island, but part of a vast, interconnected galactic ecosystem. The future of cosmic exploration is brighter than ever. The James Webb Space Telescope is still in the early years of its mission, and it will continue to unveil wonders from the deepest, darkest corners of the universe. The sky is not the limit, it is just the beginning.